Let's learn about alkaline earth metals. They belong to group 2A of long form periodic table. We have already said that S block of periodic table consists of two groups, group 1A and group 2A. Group 1A we have discussed alkali metals. This is regarding alkaline earth metals. I am going to give you the list of alkaline earth metals with their electronic configuration and atomic number. Let's make a tabular form. Element, symbol, atomic number, electronic configuration. The first element is beryllium, Be, atomic number is 4. It has got a helium core, out of which you have two more electrons present in 2s subshell. Then the next element is magnesium, Mg, atomic number 12. It has got a neon core and 3s2 electrons. Number 3, calcium, Ca, 20, argon core, 4s2. Number 4 is strontium, Sr, 38. It has got krypton core. As you know, krypton has got 36 electrons. This has got 2 extra electrons. Those are present in 5s subshell. The next element in the list is barium, Ba. This is 56. It has got xenon core and 2 electrons in the 6s subshell. The last element in the list is radium, Ra, 88. It has got radon core, 2 electrons in the 7s subshell. So this is the list of elements you have in group 2A. These elements are collectively called as alkaline earth metals. The reason is their oxides are basic and form most of the earth is it contains oxides of these metals. Look at the list once again: beryllium, magnesium, calcium, strontium, barium and radium. Remember, one important point regarding radium is the radioactive element. So when we talk about most of the physical and chemical properties of these elements, we'll be dealing with elements up to barium. Radium is not considered because its radioactive properties are more important than its physical or chemical properties. And you can realize that all of them have 2 electrons in their outermost orbit. So their general electronic configuration is ns2. General electronic configuration of these elements is ns2. So you can see the last electron or differentiating electron of these elements has entered s subshell. So they are placed in s block of long form periodic table. As they have 2 valence electrons, they are placed in group 2 of the periodic table. We'll now learn about their properties one by one. Just go through the elements once and we'll move on to the properties of these elements. Let's learn about the properties of alkaline earth metals. We'll be mostly comparing their properties with those of alkali metals. Like alkali metals, these metals are also active metals. They tend to lose electrons easily. They are highly electropositive, but these are less electropositive than alkali metals. Among these elements, beryllium, magnesium, calcium, strontium and barium, all are metals except beryllium. Beryllium is metalloid. The metalloid, only metalloid present in alkaline earth metals is beryllium. Rest of the elements are pure, pakka metal, metals. Now regarding properties, number 1, atomic and ionic radii. See, if you compare atomic and ionic radii, 2A metals are smaller than corresponding 1A metals. The size of 2A metals, whether it is ionic size or atomic size, it is less than corresponding 1A. For instance, beryllium is smaller than lithium. Similarly, magnesium is smaller than sodium of 1A group. And then down the group, size decreases, whether it is ionic size or atomic size. You can write like this: size of Be is smaller than Mg, Mg is smaller than Ca, Ca is smaller than Sr, then you have Ba. So as you can see, there is a regular increase in the size as we move down the group. This is true for even ionic size. Be2 plus is smaller than Mg2 plus, which is smaller than Ca2 plus, which is again smaller than Sr2 plus, and finally you have Ba2 plus. This is as expected, because as you go down the group, there is an increase in number of shells. Because of increase in number of shells, size increases. And also remember that any 2A metal has size smaller than corresponding 1A metal of the same period. That's about atomic and ionic size. Let's move on to the next property, metallic nature. Again remember, 2A metals are less metallic than 1A metals. When you compare metallic nature, remember that 2A metals are less metallic in nature than 1A metals. And also remember that beryllium is a metalloid. That means it has properties characteristic of both metals as well as non-metals, but it is predominantly a metal. It is having lesser properties of non-metals. It resembles more with metals. And also remember this point: metallic nature increases down the group. As you go down the group, metallic nature increases. So most metallic among them is barium. That's about metallic nature. The next property we are going to discuss is ionization enthalpy. Here also you can compare 2A and 1A metals. 2A metals have higher ionization enthalpy than corresponding 1A metals. We have already said that in any period, 1A metals have lowest ionization enthalpy. So as you move across a period, ionization enthalpy increases. Therefore, 2A metals have higher ionization enthalpy when compared to corresponding 1A metals. So if you compare beryllium and lithium, ionization enthalpy of beryllium is greater than that of lithium. Similarly, magnesium is greater than that of sodium. Ionization enthalpy, as you go down the group, there is an increase in size. Therefore, ionization enthalpy decreases down the group. So the order is like this: beryllium greater than magnesium, then you have calcium, strontium, and finally barium. This is the order of ionization enthalpy. As you go down the group, ionization enthalpy regularly decreases. It is because of increase in size which dominates over the effect of increase in nuclear charge. This comparison is required. Number 4, density. let's compare density of alkaline earth metals. First we'll compare between alkaline and earth metals and alkali metals. You'll find that alkaline earth metals are denser than corresponding alkali metals. That means lithium is less denser than beryllium, or you can put it in this way: beryllium is heavier than lithium. Similarly, magnesium of 2A group is heavier than sodium of 1A group. So any 2A metal is denser than corresponding 1A metal of the same period. Right. Now within this 2A group, as you go down the group, density first decreases up to calcium and then it increases. The order can be given like this: beryllium is greater than magnesium, magnesium is greater than calcium, calcium is less than strontium, and strontium is less than barium. So you can realize the element which has least density among them is calcium. This has a minimum value of density, whereas the element having maximum value of density is barium. It is because as you go down the group, there is a considerable increase in size from magnesium to calcium, which will outweigh the effect of increase in mass. Whereas after calcium, there is a possibility of there is a possibility of d orbital contraction in case of when you go from calcium to strontium. Even from strontium to barium also, there is a possibility of d orbital contraction, due to which the size does not increase much, atomic volume does not increase much, therefore density increases. So up to calcium there is a decrease, and beyond calcium there is an increase. It increases to such an extent that barium has the maximum density among them, and calcium is the element which has least density among group 2A. The next property we are going to discuss is regarding flame color. When compounds of alkaline earth metals are exposed to Bunsen flame, they give characteristic color to the Bunsen flame. Out of these elements, there are two elements which do not give any flame color, that is beryllium and magnesium, whereas calcium, strontium and barium compounds give characteristic color to the Bunsen flame. The color arises, as I told you in case of alkali metals, the color arises due to excitation and de-excitation of electrons. When it takes up heat from the flame and the electrons go into excited state, they come back to the ground state and lose energy in the form of radiation and give wavelengths of characteristic color. Now, the colors are like this: flame colors. All calcium compounds give brick red color to the Bunsen flame. All strontium compounds give crimson color, and barium compounds give apple green color to the Bunsen flame. These colors correspond to the wavelengths which appear due to de-excitation of electrons from excited state. When they come back to the ground state, they give rise to wavelengths corresponding to these colors. So remember, beryllium and magnesium do not give flame color. Calcium, strontium and barium give flame color. This fact is exploited in the qualitative analysis, that is detection of these elements in salts. So if you have a doubt whether the given salt is a calcium salt or not, take a pinch of it and expose it to the Bunsen flame. If you get brick red color, it must be calcium. After flame color, the next property we are going to discuss is hydration energy. Well, the next property we are going to discuss is hydration energy. We know that the alkaline earth metal has an ability to lose 2 electrons and forms a dipositive ion. This ion gets solvated. I can put it in the next equation. See, the enthalpy change for this process is the sum of sublimation energy and ionization enthalpies, two ionization enthalpies, because two electrons are being lost. We are not talking about this. Actually, we are talking about this. The transformation of gaseous dipositive ion into equated dipositive ion. This process is exothermic. So the enthalpy change involved in the transformation of 1 mole of gaseous dipositive ions into equated ions is called as hydration enthalpy. We are going to compare hydration enthalpy. See, this process involves formation of ion dipole bonds. Ion is the dipositive alkali metal ion and the dipole is water molecules. Water molecules attract this through the negative ends, that is oxygen atoms. So if you compare hydration energy, the order of hydration energy, see, I told you the process is exothermic. The reason is attraction involving negatively charged oxygen of water molecules with the positive ion. So force of attraction depends upon the charge density on the ion, which in turn depends upon its size. So as the size increases, charge density decreases, therefore ion dipole attractions become weaker. B2 plus is the smallest. That's the reason why hydration energy of beryllium is maximum. Then comes magnesium, then calcium, then strontium, and at the end you have barium. So there is a regular decrease in the hydration energy as you move from beryllium to barium cation. That's about hydration energy. Hydration energy decreases on descending down the group. It is because of increase in the size of ion and there is a corresponding decrease in the charge density. The next property is electrode potential. Here we will be comparing standard oxidation potentials, SOP values, standard oxidation potentials. See, the electrode reaction involved is M solid gives rise to M2 plus aqueous corresponding to this electrode reaction. This involves loss of 2 electrons. Corresponding to this reaction, we are going to compare electrode potential values. So the order of SOP is beryllium less than magnesium, then you have calcium, strontium, and finally you have barium. So as you go down the group, the standard oxidation potential increases. Barium has highest SOP value, standard oxidation potential. SOP stands for standard oxidation potential. It's a measure of ability of an element to undergo oxidation, measure of ability of an element to lose electrons, to get oxidized. Here this involves oxidation of metal into metal ion. So this is a measure of ability to undergo oxidation. See, if an element is capable of undergoing oxidation easily, that means it is capable of reacting as a powerful reducing agent. So the most powerful reducing agent among them is barium. Barium, due to its large size, has a great tendency to lose electrons and become Ba2 plus, and that is responsible for it to behave as the most powerful reducing agent among alkaline earth metals. Now we can discuss some chemical properties of alkaline earth metals. Let's discuss some chemical properties of alkaline earth metals.